Hello everyone, and welcome back to another engineering statics lecture video. I hope you guys are all doing well and are ready to learn perhaps what first years hate the most, three-dimensional vectors. Now, in the previous three videos, or week one videos, we spent a lot of time discussing two-dimensional vectors. We came out with some nice formulas for things like magnitude and the unit vector, and we concluded that 2D vectors, they're actually pretty nice because they're very easy to look at and visualize. If I had a vector in two dimensions, I can very easily find the angle with the x-axis. I was going to say axis, but of course that doesn't make any sense. And we can figure out things like magnitude, force components. It was all pretty simple. Now I kind of alluded to this in the last video that the next logical step was to take what we learned in two dimensions and apply them to three dimensions. So that's what we're going to be doing today. Now for those of you who are a little bit concerned saying, Clayton, I was very comfortable with 2D. It's something we covered in high school. It's something nice to me. And I'm a little bit scared at 3D. Well, don't be scared. As we're going to see, it's very simple and we actually don't have to do a lot. We just add one minor modification to everything that we do. So let's get started. So the extension from 2D to 3D may sound complex, but it's actually very simple because we're only doing one thing, and that is adding a component to our Cartesian vectors. So remember in 2D, if I had a force vector, we said that this can be split into two components, fx and fy, and I can write the vector as such, where my force vector is simply fx in the I direction plus fy in the j direction. In three dimensions, it's actually going to be the exact same thing. This three-dimensional vector can be split into three components that are parallel to each axis. So I'd have fy, fx, and of course fz. And you guys may have guessed, writing this is just as simple. It's going to be the same format as before, but the only difference is at the end we add that third component. So what we would say is we have fz in the k direction. So the k, that's going to be our third direction, if you will, and fc is going to be the components of our force in that direction. Now, the first thing that comes to 3D that students start to hate is something called the right-hand rule. Because typically what's going to happen in exam scenarios, this is a little trick for you guys, is that professors will label the x-axis and the y-axis, but they won't label the positive z-axis. Now, us as engineers, we always think, positive is always up, right? So we're thinking, we're good to go, it's always going upwards. But actually, the positive z direction follows something called the right-hand rule. Now you guys may be saying, Clayton, what the hell does that mean? Well, let's go over it. It's a series of steps. So if I want to find the positive z-axis, or if I have, let's say, the x and z-axis, I can find the positive y-axis. All I'm going to do is point my fingers in the direction of the positive x-axis. I'm going to then curl my fingers towards the positive y-axis, and whatever way my thumb is pointing is actually the direction of the positive z-axis. Now you guys may be saying, Clayton, that was garbage. I don't understand what you said at all. Can you give me an example? Well, yes, of course. That's the best way to learn these things. So let's say that in an exam scenario, you're given, again, the positive x-axis and the positive y-axis. Now, again, by default, we always assume that the positive z-axis is going to be upwards. But if we follow the right-hand rule in this scenario, so again, first step, I'm going to take my four fingers of my right hand, so make sure this is your right hand. It's called the right-hand rule for a reason. And I'm going to point my fingers at the positive x-axis. So it's kind of to the side here. Now, the second step is I want to curl my fingers towards the y-axis. So the y-axis, of course, is going this way. So I want to curl my fingers. Now notice that if I want to curl my fingers, the only logical way to do that is if my thumb is down. So in this particular case, the z-axis is actually going downwards. Because if we look, I'm curling my fingers and my thumb is pointing downwards. Notice that I can point my fingers at the x-axis, but I can't curl this way. So this is why it's not going upwards. The only way I can curl is if my thumb is going downwards. So in this particular scenario, the positive z-axis is actually going downwards. Now let's look at the opposite scenario. In this case, we flipped where the x and the y-axis are. So in this case, I'd be pointing towards the x, and I'm able to curl to the y-axis. And as we can see, my thumb is now sticking up. So again, I'm going to curl this way. My thumb is sticking up. So therefore, the positive z-axis in this case is actually upwards. Now, I'm going to give you that kind of full transparency. I like to tell you the tips and tricks. I don't know why I couldn't say that. Two T's must be a little bit hard for me today, I guess. I've very rarely seen this in an exam. It's one of those little things where it's fun to know, but rarely have I seen you guys test it on. So be aware of it, but if you guys are really struggling, don't be too scared. Something I've very rarely seen on exams. So let's talk about the other two things. So remember in 2D vectors, we said, all right, we had our Cartesian vector form. And with that, we were able to do two things. The first one is the magnitude, and then the second one is the unit vector. Well, we said in 2D, the magnitude was very simple because if I have the two components, fx and fy, well, the magnitude is just going to be through simple trigonometry. So the magnitude there is simply going to be fx squared plus fy squared added together and then square rooted. Because we have a nice right triangle here, everything works out very nicely. Well, how about in 3 dimensions? It actually follows the same logic, which is hard to believe because, again, as students, you guys are always believing that 3D is somewhat much more difficult, but it's actually not. So that's the thing we have going for it. It looks like shit, but it's actually really nice. So if we have a 3D vector like this, what we can actually do is we can start creating a series of triangles. So the first triangle I'm going to look at is in that XY plane right there. If we have a triangle in the XY plane, it has a hypotenuse, which I'm going to call fxy, because again, it's in the XY plane. If we were to do some basic trig on this triangle, remember it's a right triangle, we can figure out that fxy squared is equal to fx squared plus fy squared. The hypotenuse squared is equal to the two side lengths squared and added together. So far so good, nothing too crazy. But what else is nice is we can form a second triangle, this one going from the xy plane vertically. And again, this is also going to be a right triangle, and we can say that for this one, the magnitude of the force squared is going to be equal to fxy squared plus fz squared. Now, it looks pretty complex, but remember that fxy, we actually have a formula for it, it's above. So from there I can substitute what I got for triangle 1 into triangle 2, and I can conclude the following, where the magnitude of f is equal to the square root of fx squared plus fy squared plus fz squared. So if we compare this to the 2D case, all we did was add that extra component at the end, that fz squared. And this is where 3D actually isn't too bad, because all we're going to be doing for every scenario is just adding that extra component. And a little fun fact for you guys, you don't need to know it for this course, but if I were to extend this to 4 dimensions, 5 dimensions, all I would be doing to this formula is just tacking on that additional component squared. You guys will learn more about this in linear algebra, which I guarantee most of you will not like. Linear algebra, so it's a different type of course. It's a lot of fun. It's very useful, but it's different. I'll just say that. So we talked about magnitude. We said, easy peasy. All we have to do is add that extra component. What about the unit vectors? Clayton, surely the unit vectors must have something a little different. Well, before we talk about the formula, let's just remind ourselves what a unit vector is. Remember, in essence, a vector is a magnitude, which we discussed in the previous slide, multiplied by a direction. And in 2 dimensions, we said that that direction can be expressed as a vector, which we call the unit vector. So if this was my force vector in 3D, the unit vector is going to look something like this. It has a magnitude of 1, so it's going to be smaller than the force vector, and it has the same direction as that force vector. So there's the key, it has the same direction, and again, we use this to define the direction of that force vector. Now, the unit vector is actually really nice, because all we have to do to the formula compared to 2D is we're just going to add in that additional component. So remember, in 2 dimensions, we said that we can find this unit vector by simply dividing each one of the components by the magnitude of the force. And that same definition applies here, where all I did was I took fx and divided by the magnitude. I took fy divided by the magnitude. And now for 3 dimensions, I took fz and also divided by the magnitude. So again, same formula as 2D, we just have to add that additional component. Now, unit vectors in 3D, they maintain all of those same properties in 2D that we had. So if you guys are thinking about unit vectors, make sure you remember these 3 things. The first one is they're just used to define direction. That's it. They don't have units, nothing like that. They solely define a direction, which goes into the second point, they're unitless. So it's one of those things, if your professor wants to be an ass and you accidentally put units of, let's say, meters or feet on a unit vector, well, you're probably going to get some marks taken off, because unit vectors, they are unitless, they just define the direction. Now, the last one, which is very important, and we've talked about this already, is that they actually have a magnitude of 1. And you guys are saying, Clayton, you keep saying that and you say it's important, but we've never had to use that idea. Well, in this lecture later on, as we're going to see, this is going to become very important, not only now, but also in later topics. So always remember, unit vectors, they have a magnitude of 1. Going to come in handy. So you guys are saying, well, you know what, Clayton? 3D, you're right, it isn't too bad. All we did was add that additional component. When we talked about our force in CVN, we just added a K component. When we talked about our magnitude, we just added that FZ component squared. When we talked about our unit vector, we just added that K component. Nice and simple, right? Well, yes and no. So 3D starts to get a little bit more complex when we start talking about coordinate direction angles. So remember in 2D, if we had the two components, it was very easy to see the angle that the vector made with the x-axis. And if I knew the angle the vector made with the x-axis, it's very easy to determine what the angle the vector makes with the y-axis. I just go 90 degrees minus that angle. In 3 dimensions, it gets a little bit more tricky because we actually have 3 axes we need to consider. So coordinate direction angles are the angles a 3D vector makes with the positive axis. All right, so there's going to be the key here. These are the angles it makes with a positive axis. So let's say I had my force vector. It's looking sexy. It has all the components, fx, fy, and fz. Well, the coordinate direction angles are going to look something like this. So from the positive x-axis to our force vector, we call this angle alpha. From the positive y-axis to our vector, we call this angle beta. And then finally, from the positive z-axis to our vector, we call this angle gamma. All right? And you guys are saying, Clayton, oh, I don't like the looks of that. 3D angles, kind of gross. But here's a little secret. Coordinate direction angles are actually your best friend. They make everything as easy as it can be. The reason why? Well, we can figure out force components using these coordinate direction angles. Remember that typically we're given the magnitude of a force. We're not given the force in CVN. We're given the magnitude, some trigonometry stuff, and we're expected to figure out what the force is in CVN. If we're given coordinate direction angles, we can very easily find each one of the components because all we're going to do is take that magnitude, which we're given, and multiply it by the cosine of the coordinate direction angle. So for fx, I'm going to take my magnitude f, and I'm going to multiply it by cosine of alpha. For y, same thing, except cosine of beta. And then for z, same thing, except cosine of gamma. So notice one thing here. These are all cosines. And this will be explained right here. So a couple of little things. These angles are always going to be between 0 degrees and 180 degrees. All right? We can't have more than 180 degrees because then it starts measuring from the negative axis or the opposite way. So our angles are always going to be between 0 and 180. And this is important because this allows for our cosines to be positive or negative. So let's say that I had an axis that is positive going to the left. All right? Or I guess this is to the right. I get a little bit confused. The positive going to the right. But my force vector is actually going to the left. Well, as we can see here, the angle is going to be greater than 90 degrees. So let's say it's 120 degrees. If I cosine 120 degrees, I'm going to get a negative value. So this math right here actually takes into account direction. Because if my force is greater than 90 degrees, it'll automatically become negative, which indicates it's going in the opposite direction. So it's actually really nice for us because this allows for those negative components. As we're going to see here, a lot of the intuitiveness that we've had in 2D gets erased in 3D because the math actually starts accounting for everything we need to know, which is great. It means that we have to think less, and that's always the best solution. So coordinate direction angles. Now, coordinate direction angles actually do something very special with the unit vector. And this is trick number 1 professors love to throw at you guys at a midterm exam or even an assignment, but they usually like to save it to the exam. If they give it to you in the assignment, then you guys know the trick. If they spring it on you in the exam, well, you're kind of screwed. So this is trick number 1. Coordinate direction angles form a very special relationship with unit vectors. So if we look at our unit vector formula, it's very simple. We just take each component and divide it by the magnitude of our force. Now, we're saying, Clayton, components, we actually know what those are from the coordinate direction angles. We know that fx is going to be the magnitude multiplied by cosine alpha, fy is f multiplied by cosine beta, and fz, of course, is going to be f multiplied by cosine gamma. So if I take those identities from coordinate direction angles and substitute them into the unit vector formula, I get the following. Now it's nice here because I'm seeing a lot of magnitudes of f on the top and the bottom. So I can actually cancel those all out. If I'm taking something and dividing it by the same thing, of course it cancels out. So this formula can actually be simplified into the following, where the unit vector can actually be directly obtained just by going cosine of alpha in the I direction, cosine of beta in the j direction, and cosine of gamma in the k direction. I didn't need the force magnitude at all. I already know what my unit vector is going to be, which is great. So there's kind of the first little thing. Now, here's where the trick comes in. We know that the magnitude of a unit vector is 1. I've been saying that all the time. This is where it comes in handy for the first time. So if I look at that formula I have, and I know the magnitude of that bad boy must be 1, well, I can conclude the following, that the square root of all the components squared, so cosine squared alpha, cosine squared beta, and cosine squared gamma, if I know that that is equal to 1, I can simplify it into the following. All I do is square both sides. The square root vanishes on the left. 1 squared, well, that's still going to be 1. I get the following identity, where cosine of alpha squared plus cosine of beta squared plus cosine of gamma squared, that's all equal to 1. So this is where the trick comes in, because what professors love to do is they only give you 2 coordinate direction angles. And a lot of students will say, well, I got 2 coordinate direction angles, I can't do anything. I need that third one to actually make things meaningful. Well, if you know 2 of the angles, you can actually solve for the third one using this formula. So this is the first trick. For instance, if I know what alpha and gamma is, my only unknown in this equation is going to be beta. So I can solve for beta directly. I'm laughing. I'm in the exam, they throw the trick at me, but I know what the trick is. I'm having a great time. So that's going to be the first trick. Now, the last thing we have to discuss is solving these vector components. We went through the formula of magnitude, unit vector, and we initially had all the components. We said we have fx, fy, and fz, and if I know those 3 components, everything's easy. I just substitute everything into formulas. But remember, typically in these type of questions, we're not given the components. We're actually given the magnitude of the force and some sort of trigonometry. And as an initial step, we have to take what we know and find that force vector in Cartesian vector form. So for 3D scenarios, we have 3 general cases to find these force components. And it's not official 3 cases, it's my own personal 3 cases. So if you guys know these 3 cases, you guys will be good to go no matter what scenario. The first one is what I call the trig case, the trigonometry case. This is the one students I think hate the most because again, it's trigonometry. No one likes trigonometry. So this is the case where they give us our force vector in 3D and they give us 2 things, 2 trigonomic identities. They give us the angle from the xy plane up until the vector, so that would be theta 1 in this picture, and then they give us the angle in the xy plane, that theta 2. So in this particular case, it looks really complex, but it's actually just a matter of solving 2 right triangles. So the first triangle is going to come right here. So if I were to go from the xy plane out, we have fxy. And then if I were to go from that point upwards, it would be fz. So this is going to be our first triangle, and the angle, of course, is going to be theta 1. So from here I can conclude 2 things. My fz component is simply going to be the magnitude multiplied by sine theta 1. So that's pretty easy. Right off the bat, I already have one of my components. Now, if I were to do cosine, I'm not getting fy or fz, I'm actually getting fxy. So this would be the vector in the xy plane. And again, that's just taking the magnitude of f and multiplying it by cosine of theta 1. So at this point, I know 1 out of the 3 components. But what about the other 2? Well, these can be obtained by using the second angle, theta 2, and again creating another triangle. So I can go fx in the x direction, and then fy in the y direction, and as we can see, it forms another triangle with fxy. So in this case, my fx is going to be fxy times cosine of theta, and my fy is going to be fxy times sine of theta 2. So that fxy, even though it seems like a useless intermediate step, we actually need it to solve for fx as well as fy. At the end, this is the worst case, but it's actually pretty simple. It's just 4 calculations. You'll be good to go. You'll know all of your components, and then you can proceed to things like the unit vector, magnitude, stuff like that. Now, the second case is what I call the coordinate angles case, or the coordinate direction angles, and this is the one we just talked about. It's going to be the easier case. So this is when they give you a force vector in 3D, and they're very generous, and then they give you the 3 coordinate direction angles. If this is the case, we said, Clayton, this is a joke. We know that we can find those components if we know those coordinate direction angles. Fx is simply going to be the magnitude of f multiplied by cosine alpha. Fy is going to be the magnitude of f multiplied by cosine beta. And finally, Fz is going to be the magnitude of f multiplied by cosine gamma. So as we can see, this is actually the easier of the cases. Now remember, the only real trick that they can give you in this one is they give you 2 of the coordinate direction angles. Let's say alpha and beta. And then you're saying, okay, well, how do I find gamma? Well, remember that cosine alpha squared plus beta, cosine beta squared plus cosine gamma squared, that's all equal to 1. So if we know 2 of them, we can solve for that third angle. And once we know all 3, we can figure out every component. So these are going to be the 2 kind of main cases you're going to see initially. Now you guys are saying, Clayton, you idiot, you have a typo. You said that there's 3 cases, but you just showed us 2. Well, there actually is a third case, but it's not going to be in this video because the third case is much more different than these first 2 cases. And it uses something called position vectors, which are going to be extremely important moving forward. The reason why I'm not discussing in this video is because it's not like the first 2 cases. The first 2 cases involve trigonometry. Every single calculation here is cosine or sine of an angle. Now, this is impractical in reality. Let's say that I have a giant wire that stretches to a telephone pole, provides it some support. As an engineer, you're not going to go out in the field with your dinky little protractor and start measuring angles. You'd look like an idiot. So these 2 cases, they're good to know, but in reality, they're impractical because we don't go out into real life and start measuring angles of things. What we know are position, or coordinate points. We would know the location of something, and we would know the location of another thing. And as we're going to see in the next lecture, if we know the 2 locations, we can actually solve for components really simply. So that's a little, I'm alluding to the next video, so it's great. So for now, we need to know these 2 cases, and then we'll discuss the third case in the next video. So now that we know the components of a 3D vector, as well as the formulas for the unit vector, magnitude, and coordinate direction angles, the last thing that these questions really ask us to do is just add the vectors together. They'll give us maybe 3 vectors, and they'll say, you know what, I want that resultant vector. Well, if we have all of our vectors into Cartesian vector notation, we can add them using the same process as before, where the x component is simply going to be the summation of all the x components. The resultant y component is going to be the summation of all the y components. The only thing that we're doing is we're now adding those z components. But again, we just take them, we add them all together. Best way to show this is an example. So let's say that they give you 3 vectors, and they say, you know what, Clayton? I want that resultant vector f1 plus f2 plus f3. And you guys may be saying, oh, this looks like a lot of work. Actually, it's a piece of cake. Fr, or the resultant vector, is going to have a component in the I direction. So all I'm going to do is I'm going to take the I components of f1, f2, and f3, combine them together, and then I get 2 minus 1 plus 3. And that is going to be my resultant I component. For the j component, again, all I'm doing is I'm taking all 3 of those j components of f1, f2, and f3, adding them together, and then the same thing for the k component. So my resultant force is going to be 4i plus 2j plus 3k. And now that I know this, I can figure out the unit vector, I can figure out the magnitude, all of that fun stuff. So as we can see, it's actually looking very nice. Now, you guys are saying, Clayton, it's looking nice, but I'm not stupid. It's looking too nice. That's what you kind of learn in your later years. If something looks nice, well, there's probably something bad around the corner. And the answer is yes and no. So that's probably not the answer you guys want to hear, but that is this. Thus far, we've always just said that if we want a resultant vector, just add everything together, you're good to go. And that's true because up until this point, we've dealt with something called concurrent systems. And next week, too, we're still going to be dealing with them, so it's okay. Concurrent systems are fine. But what happens is all these systems, or all these forces, act at the same point. And this allows for all of that simplicity. This allows us to take all of our forces, add them together. Because if I take everything and I put it at the same point, this is my AirPods case, well, as we can see, this thing is just going to move nicely. All right, it remains a point. But as we're going to see in week 4 and beyond, we're going to deal with something called non-concurrent systems. And this is when our forces do not act at the same point. So it's going to be something like this. And this is where the complexity starts to happen. Because if I have a force acting at the ear and another force acting at the ass, and I were to push, as we can see, this thing starts to rotate. And that's where things are going to get a little bit more complex. So don't be alarmed that it's really easy right now, because it's going to get a little bit more complex in the future, but overall it's actually not going to be too bad. So yeah, that's it for this video. I hope you guys are nice and comfortable with 3D vectors. Again, sounds like garbage, but all we're doing is adding that extra component. In the next video, we're going to be discussing those position vectors, which is our third case to finding vector components. And then after that, I'm going to show you guys the first real examination trick. All right, so there's going to be 2 lectures that are before the midterm that always get students. And that's going to be that video coming up. And then there's going to be one later on. But we'll save that piece of trash for later, because it's probably the worst out of all engineering statics. So yep, that's it for this video. I want to thank you guys so much for listening. I really appreciate it. I hope you guys have a wonderful day, and I will see you in the next video.